Really great to have you here for this course on Docker basic concepts in configuration. The goal is to give you enough information about what makes Docker containers so good at the things they do that you'll be ready to get started with your own simple projects. You probably already know that containers are lightweight, virtualized servers that leverage the hardware resources of their host machines. Because they're completely defined by text-based scripts, their life cycles can be easily automated. Before we dive into some of the mechanics that make containers work, let me give you an actual live example. Sometimes just seeing it happen can be more effective than listening to me talking for 10 minutes. Don't worry if some stuff doesn't make sense right away. I'll explain everything later. This shell is actually running inside an Ubuntu Linux container on my own workstation. This is a single command, but I've broken up the lines to make it all easier for you to see. Let me describe what's happening here. I tell Docker to execute a run operation that'll launch an operating system image in detached mode. That means the container will come to life, but I'll immediately get back control of my command line. I'll call this container app0. The -e argument sets the time zone the container will use. I know that sounds like a minor point, but this argument actually bypasses an old bug that's been impacting Ubuntu containers for years. The -p argument sets the network ports through which external users will access the server. Since this is going to be a web server, outside clients will use port 8080, while their requests are forwarded to port 80 when they're sent to the server itself. The last line points to an online repository of an official image containing the Apache web server pre-installed on Ubuntu Linux. That'll be the base operating system running in our container. When I hit enter to run the command, Docker begins by looking for a local copy of that Ubuntu image. When it can't find anything, it heads out to the Docker Hub site and downloads the image, layer by layer. Each of the lines you're seeing here refers to a unique image layer. If I'd happened to download any one of those layers in the past, then Docker would default to those, saving time and bandwidth. Within a few seconds, everything has been downloaded, and a new container has been launched. That new container is identified by this long hexadecimal string. If everything went according to plan, there should be a web server active inside the container that I should be able to access from the outside. From the command line, I can do that using curl and specifying localhost and the 8080 port. That worked. The text that was downloaded is an HTML version of Apache's default homepage. Now I should also be able to do that from my workstation, although I'll need to use the public IP address of my Docker host. I happen to know that IP is 10.03.164. I'll add the 8080 port. And there we are. That single Docker command gave us a fully functioning website. All we need to do to make it useful is add our own content to the web root inside the container. I'll show you how all that worked in the next clip. I said earlier that containers are efficient. Well, let's see what it is that makes that so. Container technologies in general involve convincing software applications that they're sitting inside physical servers with access to all the memory, storage, and compute resources they need to operate. But in reality, they're just inside a virtual environment sharing those resources with the host computer and, potentially, dozens of other containers. This way of organizing resources lets us pack far more workloads into a single server than would otherwise be possible. It also allows us to define our workloads using software, which opens up all kinds of opportunities to automate just about anything. Also, because containers are really nothing more than scripts, you can provision and execute workloads in moments rather than weeks. Microservices architectures, for instance, will commonly launch a container to run a very specific operation and then kill it off, all within a few seconds. One more remarkable feature of containers is how a developer can build a complex application into a container image that can then be easily shared with team members and stakeholders for their feedback. An updated version of the image definition could then be deployed to production as a container, and all with complete confidence that the images will behave identically no matter where they're run. Okay, it's time we properly defined some of those moving parts. Docker Engine is the platform we use for building, running, and managing containers. It's really the entire Docker system. Docker Engine is made up of the container runtime, which is responsible for managing, creating, executing, deleting, and isolating containers for security purposes. A REST API, which allows users and tools to interact with Docker programmatically, and a command line interface through which you can use the Docker command to interact with your containers and images. There's one more important piece of the under-the-hood infrastructure, Docker daemon. It's through the Docker daemon that the Docker API and command line interface can connect with the container runtime. You might be forgiven for dismissing the daemon as something like your car's steering linkage. Sure, it's important, but you can be a great driver without knowing anything about how that works. Well, that might not be quite the same with Docker daemon, and that's because just about everything that controls your Docker environment can be customized through the daemon configuration file. It probably won't surprise you to learn that that configuration file is called daemon.json. Daemon configurations control elements like logging behavior, networking, security, and storage drivers. The Docker daemon itself relies on the host OS kernel to execute the low-level mechanics of containerization. While the daemon orchestrates and manages containers, the kernel provides the tools to actually make things happen. That might mean resource isolation to ensure users within containers can't break out and hijack other containers or even the host. It'll also involve host-based control groups to enforce limits to the system resources allocated to individual containers. All this can only happen when the daemon is running on top of a Linux host. When you want to run Docker on macOS or Windows, Docker Desktop will provision a lightweight Linux virtual machine to provide the needed Linux kernel. A Docker image is a read-only template that contains the instructions and dependencies needed to create a container. You can think of images as blueprints from which the containers are built. A container is simply a running instance of the definitions provided by a Docker image. They're lightweight and isolated environments for executing applications. A Dockerfile is a plain text file that's used as one approach to building images. Docker can read a Dockerfile and, based on the file's instructions, turn text into live infrastructure. Finally, a Docker registry is a storage and distribution system for Docker images. It hosts and manages repositories where images are stored, allowing users to push or pull their images, which allows for controlled and secure collaboration. Docker Hub is the most famous public image registry, but you're welcome to create and manage your own private and highly secure registries. Here's where we're going to explore the many approaches to installing Docker on your own machines. Later on, we'll also provision and launch a workload and experiment a bit with customizing our Docker environment. But right now, we'll tackle some complications associated with installation. The main problem is that Docker containers need the resources of specifically a Linux host to run. That means, of course, that Docker will feel the most at home on Linux. But since so many people want to use it on Windows and Mac OS, Docker developers created a graphic interface called Docker Desktop, which, in most versions at least, runs on top of a Linux virtual machine. As you can see, here's where you can download binaries to run on various flavors of Mac OS or Windows computers. Those links just trigger a download of the package you select. But you'll definitely also want to read through the guidelines and system requirements documentation. Here, for instance, is the page with all the background you'll need to get up and running on Windows. I could also install Docker Desktop on a Linux machine. And here's the documentation that'll cover you for that. Because Docker Desktop is a GUI application, it comes with some requirements that we won't have to worry about for the demos we're going to see here. And that's because we're going to be working from the command line with the open source Docker Engine. This page has all the links you'll need, including Docker Engine installation instructions for each of the major Linux distributions. I'll click the Ubuntu link because that's what we'll be working with. One of the worst causes of Docker runtime problems is elements of old Docker installations hiding on the system. So Docker documentation makes a point of showing us how to remove any leftovers. I should note that even when you're focused specifically on, say, Docker Engine and Ubuntu Linux, you'll still be faced with multiple possible paths for installation. I could, for instance, go with the Docker IO package provided by the Debian software repository. That'll be fast and simple, and it'll work. But you'll probably soon figure out that it doesn't come with all the latest features. And trust me, you don't want to go down that road. Instead, I'm going to show you one of the official Docker approaches to installation on Ubuntu systems. I created a bash script using code copied from that documentation page we just saw. Here's what that script looks like. You can copy and paste the code that's specific to your needs from the Docker Engine site. The first section installs the encryption infrastructure we'll need to ensure that the actual package we'll soon download will be secure in transit. Next, we'll add the private Docker repository to our apt sources list. That'll incorporate the upstream Docker repo into our package management system, which, among other things, means that updates and patches should be handled automatically. Finally, the script will install all the packages we'll need for our operations. We're going to get back to that Docker BuildX plugin later, but I will mention that it's one of the important components that you won't get from the Docker IO version. I'll just drop out of that and clear the screen. Now, before I can run the script, I'll have to make it executable using chmod. With that, I'm all set to run the script. This will take 30 or 40 seconds or so on my machine, although I've got a pretty good internet connection, so those downloads may be a bit longer for some of you. I'll skip through some of the process so we can stay focused on the stuff we have to do. The nice thing about scripts is that they do all the hard work for us. Once we're done, I'll clear the screen and start up the Docker daemon using systemctl. I'll then enable Docker to ensure the process starts up after a system reboot. I'll confirm that everything's running by typing status. Everything looks good. Right now, if I invoke the Docker CLI, I'll need to do it using sudo to get admin privileges. To make things a bit simpler for us over the long term, I'm going to add my user, which is called Ubuntu on this machine, to the brand new Docker system group in the etc/group file. All I need to do is type the username immediately after the end of the Docker line. Make sure you don't include any spaces on this line, by the way. And if you have more than one user to add, separate them with nothing more than a comma. That change won't take any effect until the next time my user logs into a new session. So I'll try out Docker using sudo one last time with a simple command. Docker ps will list any active container processes running on the system. Of course, there aren't any of those yet, but this does show us that Docker is up and running happily. Now we're going to write a text file that'll contain instructions Docker can use to build a new image. After building the image, we'll use it to run a new container. The name of that file, by accepted convention, is Dockerfile, and make sure that you use an uppercase D at the start. Here's what that file looks like. We begin by setting the base image to Ubuntu 24.04. I could also use just Ubuntu and the latest version will be used, but sometimes that could introduce the possibility of incompatibilities, so I'll specify a version that I know will work. I then pass a message to Ubuntu that any package installation processes should be completely hands-off. Since there's no way for us to respond with user inputs during this scripted installation, they're best avoided completely. Next, I'll prepare the apt package manager and install the Apache 2 HTTP server. Up until this point, there's nothing you haven't already seen. But the next step will copy a file called index.html that's in my current local directory and write it to the var/www/html directory inside the new image. That'll overwrite the current index.html file containing Apache's default homepage with whatever's written in the new file. I'll show you that in just a moment. This expose directive will open up port 80 once a container based on this image is launched. That means external clients will have access to the container using the HTTP port 80. The final step in the Docker file will run a command to ensure that Apache will be an active process. If we didn't do that, there wouldn't be any internal listening process inside our container, so Apache wouldn't actually do anything. Getting Docker files just right usually requires multiple rounds of experimentation. Whatever distribution you choose and whatever applications you want running in it, your image probably won't work quite right the first few times. This happens to be a pre-tested example, and a pretty simple one at that. I'll show you what's inside that index.html file. I know, it's really nothing spectacular, but it will allow us to confirm that the operation succeeded. And it also represents the idea that you can include any customizations you like inside your images. The tool we'll use to create an image from this Docker file is Docker buildx. Until recently, that would have been Docker build, but the transition to the buildx plugin is one of the reasons I recommend following the official Docker documentation for installation. I'll type buildx version to confirm that the plugin is installed and ready for us. Then I'll list all the available builder instances. There's only the default here, but you could define your own custom instances that would provide you with improved reproducibility, resource isolation, and CI/CD integration. But that's way beyond anything we'll see in this course. Okay, we're all set to build our new image. I do that with buildx build. -t points to the name and tag I want to give to the image. And that final dot is important since it tells Docker to look into the local directory for the Docker file I want it to use. This will take 20 seconds or so I'll skip us past some of the action. But if there were any problems, you'd probably want to consult the output here. When we're done, we'll be able to list all the existing images, and naturally, there's only this one. The value for tag here is latest. Because I didn't specify a tag, Docker defaults to latest. Once we have a valid image, there's nothing to prevent us from firing it up as a container. That works using Docker run. The -d tells Docker we want to be detached from the container once it's up. -p, once again, defines both the external and internal network ports. I finish up by typing the name of the image I want to use, my server in this case. And just like that, we're in business. I'll use curl to confirm that our Apache server is running. Great! Instead of the default Apache page, I get our custom index.html file. That's good. Now, just to be complete, I'll see what the web page looks like from a browser. I use the Docker host public IP address here along with port 8080. Perfect. That's what we want to see here. Now, how does it all look from inside the Docker system? Docker PS will give us the basics on our running container. The container ID here is the first dozen or so characters from that insanely long output from before. Then we're shown the name of the image the container is based on, the most recent command that was run, the time since creation and status, the network ports, and a machine-generated container name. These are always random combinations of two words, one an adjective and the other a noun. That name will be the easiest way to refer to the container. So when I want to stop the container, I'll run docker stop and then the name. By the way, Docker gives us command completion, so I don't have to type out the whole thing, just a couple of characters, and then hitting tab will often get us where we want to go. It'll take a few moments to shut everything down. When I try running Docker PS again to list my containers, there's nothing there. That's because old mystifying Yonath isn't running anymore. But if I up arrow to get the command back and add a -a flag, I get even stop containers from previous sessions. There's one more thing I'll show you right now. If you type just Docker, you'll get context-friendly documentation. If I scroll up, I'll see lists of key commands along with their descriptions. If you see something that looks like it's useful, but you don't know the full context, you can add a command to Docker like network here. That'll give you all the relevant subcommands. I'm sure you can see how helpful all that can be. Because there are so many ways to use Docker, Docker environments can get pretty complex. The out-of-the-box settings are usually going to work for getting started and for more simple deployments, but eventually you'll have to figure out how to edit your configurations. Most of those edits will happen through the daemon.json file that's stored in the etc docker directory. The problem, as you can see when I try to list the contents of that directory, is that there usually won't be any such file in a new installation. Of course, you're welcome to create your own containing any changes you need. But before I show you how to do that, I should show you how to find your current settings. That'll happen through the docker info command. You can see information on the host system, the Docker document root, and your security profile. Moving back up through the output, there's confirmation that two plugins are available, buildx and compose, and some basic Docker environment settings. Naturally, You can use regular bash tools like grep to filter that output. I want to print only information on the current storage driver setting. You can ignore those two warning lines. They're only included with the grep output because Docker info prints them to standard error, but they don't concern us. What does interest us is the fact that we're using the overlay 2 storage driver. There are other drivers available like AUFS, BetterFS, or when overlay 2 isn't supported by your system, device mapper. But overlay 2 is going to be your choice nearly every time. Filtering for networks. We're given a list of all the network types that are available to us. Bridge networks allow containers on a single host to communicate with each other while isolating them from the rest of the world.